videos there, but yeah, so that way this will be the third session in terms of the continuity more from the content wise.
So we'll have three only, or
One more we have that is on Sunday.
would we have the
On
fourth one sometime?
yes.
So, sir, actually, what has happened is our batch was already very small, and now NMIMS, due to some UGC regulation issues, they cancelled the registration of the three people, the Moghna, Anaida, and Satya.
Okay.
And
Sorry, I didn't knew that. Yeah.
yeah, so apart from me, there are only two people, and I mean,
No
they aren't
issues.
able to join
Yeah.
the live session.
No, things
So
will
I
be
guess
all
I
right.
don't know.
Yeah. So let's focus on the studies here. Not an issue. I hope, yes, tomorrow I will be able to find the other two no participants also here in the class. So hope for
Yes.
the best. And so
So
just yeah, please.
I just wanted to say that I find statistics very difficult.
No,
I
no, no issues, no issues. Yeah, that's why I will move in that pace only, right? So uh, just okay, then let me just start with the five number summary. Is it clear to you? Because that must be there in your uh, the async content also, right? And uh, did you find any difficulty with that? So if
um,
you want me to repeat it here, I will start from there, and then we will come to the box plot.
yeah, sir, actually, I haven't gotten a chance to do
Okay.
the async on fully yet. So that's the reason I'm not aware of a lot of it. I'm not well, and
Uh, so
I'm
no issues. Then we will move back to the previous slide, and no, then we will move accordingly, right? Because you are the only student, and I want you to understand, right? Whatever I'm teaching in this 2 hours. So let's start from here. So this is basically a data set of 70 different people. We'll do it on Excel also, okay? Slightly later on. But let me just tell you what this data is talking about. Uh, so when we start with the five number summary, okay, so in the five number summary, we have to arrange the data in either ascending or descending order. So whatever data that we get. For example, here, the they have discussed in this one, the 70 efficient apartments were random sample in a small college town, and the monthly rent prices for these apartments are listed in ascending order in the next slide. So here, what has happened? Basically, this whatever is this university data that you are finding in the next slide uh, are some kind of monthly rental price values. And as a decision maker, right, if you're just thinking of going to abroad and you want to rent out any of these places, and before that, you want to really make a mind, right, how the data is. Should I jump quickly with the decision of renting an apartment, or should I wait? Because what happens if the data is not symmetric, if it's skewed, right, towards the right hand side, the more you will delay, the higher you have to pay, right? So the prices will increase in a exponential way. Uh, but if it's on the lower side, if it's skewed to the left side, right? So the increment of the rents will be quite gradual and slow. So you want to understand that how is this, right? Entire distribution, and for that, we will try this five number. So the smallest value of the data set. What is the first quartile? Harshita, you have any idea about what are quartiles?
yes, sir.
Yes, right?
Yeah.
The first quartile is where you end with the 25% of the data, median is the second quartile, where you end with the 50% of the data. Third quartile, where you end with the 75% of the data, and the largest value is the highest charge or highest monthly rent price. Okay. So to understand this is the data that we have. 70 data, each row comprises of 10, and then there are 7 rows. So total 70 price values are here. So the lowest price value of the rentals here is 425. Then the very next is my first quartile value we have got, that is 445, right? So how we can use the Excel function for calculating the first quartile, or you can use the formula also, which is P by 100 into P is my percentile, right? So that is 25th percentile by 100 into how many? It's 70, right? So 25 by 100 into 70 values will give you the position. So if we calculate that, 25 by 100 into 70. So basically this will come as
How did we get 70?
70 are total data values. Okay, so there are total 70 rents I have. So 10 here, each row 10, okay, like that, till down 10 if you just add. So 1, 2, 3, 4, 5, 6, 7. So 10 into 7, 70. Clear? So this will be nothing but 70 by 4. And 70 by 4 is something like 1. This is then 30 means 70.
17.5.
5. Yeah. So we have to always remember that we have to round it up. Okay, in terms of position. So this is 18th. So whatever is my 18th value will be the first quartile. So this row we know that there are 10, then 11, 12, 13, 14, 15, 16, 17. Right? So that's how we got this as the first quartile value same.
Okay.
Yeah.
So in general, we have to arrange the values in ascending order, right? And then
yes. Yeah. Basically, if you are arranging in descending, means your third quartile will come first, and then the sequence will change.
Okay.
Nothing wrong, but the sequence of getting the values, because you are starting from the largest value and you're going downwards. But the value will come the same thing. Your first quartile, third quartile, median, lowest, highest, everything will be same. But you will get it in a different order. That's the only problem. Okay.
Okay. Got it.
So, and also another thing to remember, if this value that we got here, if it's a pure integer value, right? Instead of 17, if you had, 17.5, if you had got it as 70, then we have to take the average of the position of the 17th and 18th. Okay. So whatever was here as a value and this, so my percentile value or quartile value will be the average of this. Okay. But here, fortunately, these two values are same. There is no difference. We'll see if we, while doing the, anyway, the third quartile will also be a decimal value only because the number is 70. So no issues. I'm just telling you, right, how we normally we have to calculate it. So just remember the formula. If you're not getting, if you're getting a round number, then you have to take the average of the positional value of that level. Means if this is I and I plus 1. Okay. So just take the average of those two values, you will get the median value. Okay. So let me just clear all this. Same way we got the median value. This is where we have to take the average of these two value. Let's calculate it. Why this was taken, the same formula. $50 by 100 okay into 70.
Median is the second quartile.
This for the second quartile for the mean. So you're getting the value is 35, right? So which is an integer. So when you get an integer value, you have to take the positional value of 35th and 36th and divide it by 2. So you have to take the average of. So this is my 35th number. And this is my 36. So we are dividing it, but anyway, these two values are same because the whole logic of it is we are dividing it into two parts, right? So if I'm taking this as my middle value, then this side number will be more compared to this side. Okay. Same way, if I take this one, so I will have more number on the lower side compared to the higher side. That's why this is the border. Okay. So each side we have equal number of items. So basically here in this case, we were lucky that both the numbers are same. But if this value was 470 and this is 475, then the median will come as 470, 2.5. Okay, in that case. Yeah.
Got it.
So we got the median value, that is 475. Likewise, we got the third quartile as 525 and the largest value as 615. So now the concern that the portion that we had in the very start of doing this research is, if I'm delaying, okay, so do I have to pay a very high price for that delay? So if how I can find that, so I will see the left hand side how the distribution is changing. So if I compare this 425 with respect to 475, so till half the people they book the house, uh, the flat rate changes around $50 or 50 pounds to 50 euros, whatever you can call. But after that, if you see in the remaining 50% of the people, right? So that is the 35, next 35. If you compare that 615 and 425, sorry, 475, that is almost like price, this difference of 4 times different, right? You will notice. So till the median, the prices were not, or the rentals were not going so high, but once half the flats are booked, then you can see there is a fast increase, right? In fact, the next 25% increase is much faster compared to this initial 50% of the people who were booked. And further, you will see the remaining last 25 has gone up even more steeper. Yep. So that gives an indication that what is the right time when I should book the because what happens, take the example of students who go abroad for the MS or higher studies. So they might be looking for multiple university offers. Uh, so, but at the same time, if they delay that, right, booking a some kind of a hostel nearby or something, so they have to see what kind of price trade-off that could be. So really, they will be paying a huge price if they are not taking the flat immediately, or even if they delay the decision of booking the flat or the hostel room, still it's fine for that. Okay. Uh, Something that we tried to look here, uh, but it was in a number form. If we want to put it in a visual form, and again, what level it's like a outlier kind of thing, right? Is there something what is really a few people who have just charged very high rental, or it's a general trend of that, right? After the median, 50% people books, the price highs happens at a steeper rate. Uh, just to understand that, we have to go to the next one, that is the box plot. So box plot just it doesn't gives you the five number summary, but it gives you one thing more beyond that. That is the outlier values. How many values are outlier? So you can always ignore them while taking your decision. In the box plot, the very first box that you can see, this is a scale of all the rental values from the smallest to the largest. We have just created a scale. And a box plot, you can see, or you can plot it horizontally or vertically, right? So any of the ways you can plot it. So this is a horizontal box plot, but you can find a lot of places they have used even vertical box plots. So now in the box plot, the box is the first thing that comes, and then there is a partition which comes here. Okay. So within the box, the first edge of the box, okay, is Q1, and the final edge of the box is Q3, and the partition is Q2. So within your middle 50% of the data, you can see that the Q2 is much closer to the Q1. That means from Q2 to Q3, the change is much higher or much steeper. Okay, so the price change, if you are looking at here, so almost this change from Q2 to Q3 is double of what has changed between Q1 and Q2. So the first visual that tells you something about the prices, right? How it's rising once the occupancy reaches to 50% of the students, right? Now, further, we want to see if there are some outlier cases or not. And for calculating the outlier, there is a simple formula that you should remember. So outlier is the range, okay, range from Q1 and Q3, from Q1 on the downward side and from Q3 on the upward side. And this value should be up to 1.5 IQR. IQR stands for interquartile range, which is nothing but 1.5 times of the difference between Q3 and Q4, sorry, Q1, or the length of the box. This entire thing is this, and we call it as IQR, okay, interquartile range. So it's always relative, okay. So if from here I will draw a line, so we call it as whisker line. Actually, originally it was dotted line, and same way this side also will draw a whisker line, and the limit of it is 1.5 the area of, or sorry, the length of this box. But if I don't have any lower value, which is beyond that, or at that point, I will stop whatever is the lowest value. Okay. So I have to look for the dotted line. The maximum length of the dotted line will be 1.5 IQR, but that is the maximum possible length. Okay. The length of the line can stop at a smaller value also, and that is if it's the lowest value. Okay. Same way, this can go up to the the level of IQR 1.5 IQR, but if the largest value is within that 1.5 IQR, I have to stop the line there itself. I will not draw it till 1.5 IQR. So what is my IQR value here? Interquartile range 525 minus 445. So how much that is?
525 minus 445.
Yeah, 80.
85 plus 88.
Yeah.
Hmm.
So, sorry, this should be 80. Now, 450 minus 80, how much it comes?
450 minus
80.
it would be 370.
370, right? So this can go up to 370, but what is my lowest value?
425.
425. So I will not go up to 370. I will just stop here at 1 minute. I'm just I will stop at 425 only, okay? So what it means is it tells you that there is no outlier on the lower side. Now look at the upper side where we have to add 80 to 425. So where it ends, if I, sorry, 525 plus 80, my bad. So 525 plus 80, which is 605, right?
Hmm.
So my line will go up to 605 here, and I will stop. But what is the highest value?
615.
Okay, so 1 minute. Let me just go back and check. 615, right? So there are two 615. So what I will do here is there are two outliers and I have to mark two cross marks at the 615. Okay, so this box plot, what it tells me that there are two outlier values which are two extremes, right? So, and that is the first thing we got to know, which was not really reflecting in the 5-number summary. The second thing what we got to know is you see the difference. Okay, the entire data is divided into 4 parts. Lowest to this one, right? So 25% of the data is this. And the next 25% of the things, there is not much difference in terms of this distance, that right? But after that, you can see there is a huge change, right? So first 50%, and that happens even if you go to book a flat in anywhere. Like if you are looking for a property, let's say a Lodha property, and somewhere, no, in Panvel or anywhere it's coming up. First 50%, they will not raise the prices so quickly. So they will be giving discount, they will be looking for that. But the minute that they get the first 50% of booking, then the rates or the charges or square feet charges will increase in an exponential way. And that's what you are seeing here. And then the final few couple of flats will be quite outlier that will not even fit into this box plot. So they will be very different, right? And those are the HNIs, or those are the people who have to book for some good views or something very different. Clear?
Yeah.
Got it right how this box plot works. So In fact, I have one small case also. I will show you that to get an understanding with the stock market data. So whatever we had discussed, sorry, how come I 525 plus, just let's see what is the issue here. What is the IQ we got at 75? Oh, my bad. We missed out to multiply that 1.5. Sorry. Right. So for lower limit, we just added 80 there, right here, while looking for those outliers. It should be 1.5 times from the lower limit, not just IQR. Okay. That way, there was no outlier basically, but still, uh, line should have gone up to 625. I'm just correcting it. So we had to take 1.5 times of the IQR value, not just the IQR from the lower limit and upper limit. So, and any idea why this is 1.5 IQR they have allowed? How this 1.5 deviation has come?
No.
So again, this depends on like when you had studied this P sigma or when we had studied about the Six Sigma and so on. So normally what we assume that this distance will be the maximum tolerable distance will be 1.5 of the data will fall here and the balance deviation of 1.5 will be on that side. So that's how they allow that. Means approximately 3 sigma of deviation. Um, so all this are just like when Six Sigma came, they doubled it from 3 to 6. And when we take the box plot, we just take half of that 3. Okay, so that's how that 3 word which was given, right, which approximately covers based on uh, the last time when we had done that empirical rule. It says that approximately 99.7% of things will fall within that 3. So that's how this is taken, right? So means it will ideally it will cover very close to 100%, but if there is some kind of outlier that will not fit into that 100% of my no that tape that I was looking for. So these are some reasons why we should be plotting the box plot first. Because most of the statistical tests that you will do right in future, when you will learn the machine learning algorithms such as logistic regression or support vector machines or decision trees, everything goes with one assumption that the data is parametric, and parametric means the data is distributed in a normal state. Okay, so the left hand side from the median is just a mirror image of the right hand side of the data which is falling in the box plot. That is what it assumes. But in reality, we don't find most such cases, and we will understand then what to do if that is the case, because all these models assume that the data is a bell-shaped or normal data. Okay, so we have to do some kind of treatment based on the distribution that we found. Box plot is one of such descriptive statistics which can tell you, right, what amount of deviation or what amount of this data is non-parametric in nature. Clear? And then what treatment needs to be given. So this helps you in understanding the degree of spread or skewness of the data. And at the same time, it also helps you in finding the outliers, which are very different. Okay. So in a class, you have conducted a test and then you realize that Most of the students have scored between 50 to 70 marks, but there is a student or a couple of students they have scored 80 or 90 marks, okay, or slightly higher than 90 marks. So that gives you a signal, right? How come that when no, all the students are same in the class and they have performed something, and why some a couple of students have done differently? And when you will go for the inquiry, probably will find that the students had some no elder brothers or sisters who have studied from the same teacher, and they knew what questions normally I ask in different period of time. They only prepared those questions and they were thorough with that. So with less preparation, they were able to score more marks, whereas others didn't. So that I will get to know. So then I had to give them some different tests to really judge their level of learning or so on. Clear? So that gives you those indication that yes, why somebody is different, right? So and it's quite unnatural. So naturally you should be very similar, right? If you are part of the class, if you have taken the studies in the same manner. Same is the possibility of somebody scoring very less marks. And then you can look what has really happened. So probably then you will find that that day this boy was not well, no, and he was under medicine and he was not properly prepared. So you have to give him a second chance. So uh, just to understand, right, how good he or she can in terms of the studies. So those are the indicators basically, right? And a box plot can help you in identifying or giving those indications. And this I've already said they can be horizontal or vertical. I'm not taking you through the quiz now. This you can try in your free time. So one thing that I had said, I will show you this box plot which was shared with you all. This is the data of Tata Motors. Okay, so I had taken long back 3 months Tata Motors returns in the market. Okay, NSC from NSC, this data was big. And whatever we discussed, we just applied everything here. And uh, in this box plot, so we when we were drawing, we just did a horizontal box plot. So this is a vertical box plot, same thing. Lowest value here, the quarter one value here, the Q2 value is the long line, the Q3 value and the Q4, sorry, Q3 value and the highest value. But this highest value is not your highest data value. It's the within that 1.5 IQR, whatever is the highest value that you have put, and then you have all this extraordinary
Sir,
return.
are you on box plot slide? Um,
No, I'm on a Word document. Is it not visible?
no, I'm.
Okay, sorry. Good that you told me. I'm just making a. I think. Is it visible now?
Yes.
Yeah. Sorry, man. Uh, Again, I'm just making a repeat here. This is 3 months Tata Motors returns in the market. Okay, and the data is collected from the NSE website. And I want to understand because I'm interested in Tata Motors. Tata Motors is really doing good. They have become the second largest vehicle sellers in the market. So I'm quite interested in investing in the stocks of Tata Motors, but I am also slightly skeptical about their consistency in the performance wise. So just taken the data of this from the NSE website, use the Minitab software to plot it in a box plot. Okay. So the Minitab is a wonderful software. You can try 30 days trial you can get. So most of the things related to the Six Sigma uh, tools you can use Minitab for doing so. like you can have a cement leaf plot using Minitab, you can have this box plot. Nowadays, even Excel gives you the box plot, the new versions of Excel, I think after 2020. So you can plot box plot using Excel also. But I don't have the latest version of MS Excel, so this was on Minitab. So if you look at here, so we saw something in a horizontal form here. It's a vertical form of box plot. By the way, you can also draw box plots in Tableau. You can draw it in Power BI. Even if you try to know the SaaS software, right? So SaaS uh, VA, there is SaaS Visual Analytics is there. In that also you can plot box plots. There are multiple softwares which can be used for plotting it. Here, in this case, even as simple as R and Python also can be used. So tidyverse, if you use for R, that can also give you the box plot. But now, just to understand what it says here, because I want to see how good in terms of the spread of this entire Tata Motor shares over a period of time. So if you look at this data, I'm just making it slightly bigger. So this data is of previous closing, okay? So I've just taken that because when you pick the NSE, you get 4 different values of the price: opening price, closing price, then the highest of the day, the lowest of the day, like that. So I've just taken the previous close prices and it plotted. So you can see the lowest value here. From there, the one value. So obviously the median is slightly towards the lower side, that is on closer to the quarter one. Then from there, again, the distance from the Q2 to the Q3, you can see it's almost double of this distance, right? Q1 and Q2. So that gives you a hint that the data is slightly skewed. Uh, then further, when we look, the the whisker length on the upper side, that is even longer compared to the lower side whisker, but not too different. Uh, so that gives me a little confidence here on this stock. And then if I look at the outliers, again, you can see the Minitab. What it does is it gives you different, again, categorization of the outlier. Again, from here, the next 1.5 IQR, it will go in a circle form, and then there are super outliers, which will be the stars. Okay, so just to distinguish between them. And it also tells you which number of the data is this. So you can see that as the dates which are towards the upper side, right? So the 40th day, then the 57 day or 58 day and the 60th day, which are more closer to the current date, they have given supernormal values compared to the dates which are slightly older. So that gives me a little more confidence on uh, this stock, but at the same time, it gives me a signal also, a caution signal that it might be overvalued also, because all these super returns are quite recent and people have already noticed and they have already invested in this stock. So probably the price that I have to pay for this stock could be slightly at a higher level, right? It could be more than what is the face or the intrinsic value, right? The face value uh, or the market value, rather, I should say, looks a little higher. This could be overvalued stock in today's time. Yeah, so like that, you can utilize this box plot kind of things to just to understand what it means. Let's not go into all these questions. You can try and think to address them because this data is this paper is already shared with you all. So just see if you find any doubts, any queries in understanding this, you can just post it in post my query. Uh, so is it clear, Hasita, the box plot concept?
Yes, so somewhat. I think if I do async, it will be a little bit more clear.
Done, done, done. Sure.
So all the things we are learning, they're all there in the async as well, right?
It's there in the thing. And I'm uh, just because this should have been already covered because your the second assessment
Yeah, yeah. Yes, sir. Yeah.
has
So,
already covered this because this is the descriptive statistics part. Okay.
yeah.
So let's try one more time. Just look because this box plot is there. I can tell you very clearly that it's covered in
I saw in the transcript it's there.
the right.
I mean, I just want to be a lot more clear about this, so I'll watch async and then once again I'll watch the recording of this session. So maybe it will
Done,
be
done,
a
done.
lot more clear.
Sure, sure. Okay, so now I'm back to the slides and I'm in the session three slide in physical statistics. If you can just confirm it's visible or no, I think not at
Yeah.
1 minute. I'm just doing the screen share now. Yeah. Hope now it's visible, the session three in physical statistics.
Yes, yes, it's visible.
So from here on, whatever things you will do in the subsequent courses, right? Uh, more related to analytics. For this part of the discussion that we will have is very important. As I have already said, every higher order modeling algorithm, so which are very common and most widely used in the machine learning and AI area, they assume that the data will be in a shape of normally distributed,
Yeah.
right? The normal curve will be followed, but it's not always the case. So what needs to be done? And a very common term that you will come across in future is bootstrapping. Have you come across this word,
Sir, what
bootstrapping?
bootstrapping? I have heard the term.
But that is a very different context. So bootstrapping, what people normally use, right? When you come with a startup idea,
Yeah, exactly.
right? So when you come with a startup idea and when you go to an angel investor, venture capitalist, and they will ask you this question, right? What is your bootstrapping? So that
Yeah,
means how much you have invested
correct.
from your own. But when it comes to this kind of a statistical test, what we do, it means a very different from what we have till now, what we have heard in the common panels and different places. What we used to call there, right? Bootstrapping is very different here. Bootstrapping is how many samples you're creating, right? In a sampling distribution. And the reason why we have to create multiple samples because one sample may not be the correct one. And the software will ask you. So ideally, there are no different softwares. They say that around 300 is a good number of subsamples if you create within the sample or within the population that you have. Uh, we will understand that, right, as we'll progress through this session. Uh, so what is the sampling distribution? Any idea?
Um,
So we have studied probability distribution, right? You are
yeah,
clear with that probability distribution. Any doubts?
yeah, yeah. It's good.
That is clear, right? Probability distribution to you.
Yes,
So the distribution of all possible values is a probability distribution, right?
correct. Yes,
So the IPLs are going on and whatever are the possible scores, right, of different players. If I just try to put that in a simple distribution form. So let's say Rohit Sharma, he can be out in 0 or he can also have a 100, right? And in between, he has 4 different values. So, so the chance of his score in today's match could be ranging from 0 to 100, but I'm not sure. what it is, right? And in between, whatever is that is the average value, that is the mean value. So you might have scored something around 40. Is my so this is how uh, it's a distribution, right? But what happens when we try to do some kind of analysis, when we try to use samples for prediction? So uh, what normally we do is, let's take a different example beyond Rohit Sharma. So this is the distribution of Rohit Sharma, like that. We can have different distributions of different players. And now I can have all the 10 players distribution of their score. Now, for a specific day's match, if I want to predict based on different performance, what would be the total score of Mumbai Indians? So what I have to do is when I'm running that algorithm, the machine learning algorithm, so I have I cannot go with the full population data of Rohit Sharma, full population data of Ishan Kishan or some other player. I will be picking the samples. But when I'm picking the sample, what can happen? Those days could be falling here also. Those days could be falling here also, or those days could be falling here also, right? With the same average. But here, if I take the sample average, this is where it will, which is less than 40. Here, it can say something related to 65. So what is going to happen is when I'm taking randomly a sample out of the population, and I'm not taking the full population, the data could be misleading, right, in terms of predicting my total score for Mumbai Indian. So what we do is, for getting a better prediction, we randomly pick multiple samples. Okay, so this sample, this sample, this sample. Same way for every player, we will have multiple samples, and then we will run the machine learning algorithm. So we will get something value prediction where it's picked from here. Something will come from where it's picked from here. Some value will come from picked from here. And finally, like that, I will have hundreds of values. Okay. So when I take the average of all such values, so I will get exactly the value what I meant. Okay. That is the population mean, because some values will be picked from this side, some will be picked from this side. So my solution that I will get as a algorithm make answer for the prediction of the total team score based on different player, because the samples are taken instead of the population, and sample could be biased, right? So it could be from any of the sites, but when I'm taking the average of all samples, that is what is the central limit theorem says, that rather than taking a single sample for decision making, use multiple samples, okay, for a forecast, and then take the average of it, and whatever you will get will exactly give you a very similar findings what you could have taken the full population. Got it? So that is the logic why we should understand the sampling distribution, because we cannot collect the data of the full population. Okay, so definitely we have to deal with some samples, and we have to manage, but don't just blindly go with one sample, because when you're going with one sample, it could be from any side of the population. It may or may not be a true representation of the population, and that can bring some kind of error in your final decision making. So take multiple samples. So that's where we use the bootstrapping word. So how many samples you're taking from each of this data that you have taken for your decision making. So some softwares, different statisticians have different calculations. They think that 300 such subsamples could be a good thing, or anything more than 300 can give you a very precise answer or very high accurate forecast. Okay. But let's try and understand what is the sampling distribution in more detailed manner. Sampling distribution is basically you are taking different samples and you are summarizing the samples either by the mean or the standard deviation. And then you are plotting it. Right now, from one population, if you have taken 50 samples, And how will you plot those 50 samples in any distribution? By taking the mean of those 50 samples or the standard deviation. And when you're plotting it, definitely all the means will not be same, right? For all the samples, we saw that. In all the standard deviation will not be also same for every sample. So, but when we take the average of the means of all such means that we have taken, and when we take the average of all those standard deviation that we have taken, it will more or less, it will reflect the population mean and population standard deviation. So that's what the sampling distribution means. Like simple example, in any organization or in any company, they do this quality check. Yes, think about Dell, which makes laptop.
Yeah.
So you cannot look or check each and every laptop because you require that many number of manpower, and that much of time will go, and that will slow down your process, right? Time to the customer, that cycle time will slow down. So what they do the sampling. So they will pick some randomly some laptops and they will do the testing, and then they will check whether there are any defects, and accordingly they will okay that lot that yeah, there are no real defects. So like that they will be doing it every day. And when you look at their distribution, right, the number of defects and so on, because so many samples they have taken from last 15 or 20 years, that what they have been doing it for uh, the manufacturing laptop. So basically what you can say that the average number of errors that you can get from the samples using those distributions will be more or less what is the entire population, the number of defects, what you could have got. Clear? So that's how it's assumed that when we plot the average of samples as a distribution form, it reflects if the samples are too many, okay, there needs to be a good number of samples that we have to take, and also the sample size should be good. You can't have 2 item samples or 3 item samples, then it will be quite misleading. So we'll see the central limit theorem, which says what is the ideal size of sample, what number of samples you should be looking for, and so on. Okay. So sampling distribution is basically it's the distribution of the means of the samples or the distribution of the standard deviation of the samples. If it's a discrete distribution, it's the values of those defects, right? So number of defects as a number, okay, which may not be mean or a standard deviation. It's just a pure number in every lot. How many defects we have got? So that is the proportion, what we call. So it could be a distribution of the proportion. And now when we use the sampling distribution, we don't use the term standard deviation. We call it as the standard error. Okay. So the sample statistic, so the distribution of the sample means or sample standard deviation when we plot. So whatever is the mean of the population, and in that, if we look for any sample mean, whatever is the difference, it's known as the standard error. So that is the error that you have got in the sample. Okay, so that much it's deviating from the population mean, or that much it's deviating from the population standard deviation. Okay, so that's where the terms are different, right? When we deal with sampling distribution, you will not get the term standard deviation, rather we use the term standard error. Okay, so we'll see how it's calculated from the standard deviation. So now, two things which are very important here. So if you are doing the sampling from a normal population, so what is normal population? The left hand side shape is a mirror image of your right hand side of the distribution. Okay, so that is the normal population where there is no skewness. Your box plot is showing you equal divisions at every level. So in such cases, the sampling distribution of the sample mean will follow normal distribution. Okay, so when I plot all the uh, the samples mean in a distribution form, it will look very normal. And the mean of sample distribution is exactly the mean of the population. That's why it's showing mu. There is no deviation. And the standard error, because here we will not talk about standard deviation, it's the standard error. And because it's a normal distribution, so the things will be, and it's a sampling mean, the things will come much closer to the mean. And that's why the standard error value, you can calculate it by dividing the population standard deviation by root over n. And this is why your sample size is important. The larger the sample size, the lesser will be the error in your uh, that mean or the standard deviation of the sample. Okay, so if it's very big, then the standard error value will be negligible, right? It will be very close to zero. Okay, so that's how it means. The larger, that's why it say that the sample should be much larger, so you don't make any mistakes or any errors in your decisions, right? It will be as accurate as taking the entire population into consideration. So today, very interestingly, we got the poll results of Karnataka state, and a lot of news channels, they were very proudly they were claiming that their exit poll results or whatever predictions they had are 100% accurate or very close to the actuals. So what they have done, basically, whatever this exit polls were, they were sampling distributions, okay? And whatever they had predicted, right? So the kind of predictions are getting more and more accurate nowadays compared to something like 10 years or 15 years back. So something was predicted, and I still remember in 2003 or 4 election. So, so every news channel was wrong in the exit poll that time. What happened, and the government changed. But now that is not happening because so many algorithms have come up, so much of improvements have taken place, in accurately predicting what is the mandate of the people. So that's how they're getting very accurate, and 90 to 95% news channels predictions have come true. Uh, that's what is here the case, right? Where the data is quite normal and they have taken sufficiently large opinion, right, in the opinion polls after the exit poll or during that exit poll. That has really gave them a higher degree of accuracy. But again, there is a chance that whatever they have done, uh, because this was a convenient sample, so you cannot reach out in exactly in that same randomness how the people have. You might have gone to more number of males compared to more number of females because males are who can openly, who can come out, who can discuss. Females are quite reserved. Uh, that could be one case here. Same way the aged people, right? More elder people, you may not reach out. It's you might have gone to people who are very youngsters while you are collecting the samples for your opinion or exit polls. But still, you got the correct answer or correct prediction. So that was the case of the second one when the data was not normal, right? So your number of people whom you have collected for your sample was not a true representation of the population because somewhat skewed, right? You were not able to reach out that many number of older people, that many women or people who are in the remote part of the countries, right? So because you have to come with this finding very quickly. And if you're reaching out to each and every village to get those opinions, it could have taken a very long time. Definitely the sample was non-normal. It was not a bell shape. So that the central limit theorem comes into application, which helps you in identifying what is that right size of sample that should be picked in such cases so that you get a high degree of accuracy in your results. and how it should be, how many such samples need to be taken. So we'll learn that what is the central limit theorem in the next slide. So the central limit theorem, it helps you to use samples to infer or help you to use samples for coming out with a prediction or a decision for the entire population parameter. But what is that logic that it gives you or it says here? If you look at the picture, this is something what it says. This is your entire population distribution. Okay, so you can see the amount of spread this has. But from this, if I have to do the calculation, there are a lot of issues. First thing is it will take a lot of time to get that number of people opinion, and then there are a wide variety of people, right? Extremes here, either of the side. I have to deal with them, then my calculations will no issues, Harshita, that's perfectly okay. So those are some concerns, right? So to overcome that, what is done here, we have picked different samples and we have plotted. X bar is the mean of each sample. Okay, X bar tells you the mean. Okay, and of sample, mu stands for the mean of population. And when I plot the distribution of different X bars, right? This is what it is, X bar distribution, and here it's the mean X distribution. Okay, X is the actual value, but here the sample average distribution I'm doing. My spread is much less because my means will definitely tend to come more closer to the population because I'm averaging it out, right? So some values which are in this extreme will be averaged out with the ones which are on this extreme, and this scale will get shorter. The same is on the right hand side. So my peak will go up and my spread will come closer. So ideally, if all my samples are perfect, right? So then there should not be any distribution. Everything will be on the straight line. But irrespective of what you do, the samples will always carry or bring some bias in that. So you have to take more than one sample with the same kind of data and then try to find what they're saying, and that will give you exactly the prediction of this average. Okay. So that's what is the central limit theorem. So central limit theorem talks about two things. One, it says because this standard error is root of standard deviation by root n. So what is the right number of the size of the sample which can reduce your standard error significantly, right? Or within the control level. And same way, when it comes to the proportions, right? When you are not dealing with a normal distribution, but rather it's a discrete distribution, the standard error is calculated by root PQ by N. Just remember, or go back to the binomial distribution formula where we had this CR into P to the power of N and then Q to the power of N minus R, right? So that will be the binomial distribution. So P and Q, P is the chances of success and Q is the chance of failure. I mean, Q is always 1 minus P. Okay, so the mean is calculated using that root over PQ in that case, but here because it's a standard error, we are dividing by root n also. What the central limit theorem says that when your sample size increases, okay, so then whatever distribution you plot using the sampling distribution, it will be a normal distribution, irrespective of what is the distribution of your original population. Okay, so your original population could be a non-normal distribution, but when you take sufficient number of samples out of it, and then you take the means of those samples and you use them for doing the prediction, then it will give a higher degree of accuracy because that distribution is a normal distribution. So I'm telling you what challenges we used to face 20 years back with SPSS and the other softwares, right? Which were those days, because we didn't have this provision of bootstrapping or making subsamples out of the data. So you have to, if you're looking for the relationship of Y with X, so as simple as how it's predicted, I'm just showing you. There are two sets of data, and this is the distribution of the independent variable, that is X. And then you will plot the distribution of Y. Okay. And then you will look at the commonality. So this much of area is common, means that much of Y is predicted by this X variable. Okay. So this is a case of normal distribution, right? If both are normal. But what if this, for the same thing, if my Y is not normal? So I have a longer tail this side. Then you will find a smaller amount of overlap. Okay. So that could be something which is misleading. So, and to overcome that, what we used to do is, in those days, we have to do some treatments with the data. You have to take the log of the data. You have to take the exponential power of 2, power of 3, just to reduce the length of the tail. So more and more data comes here, and then you can superimpose it. That was how things were done. But now, with softwares like Smart PLS and other tools, which gives you this provision of doing the bootstrapping within that, there it creates multiple samples, and it, rather than using the pure data that you've collected, it will use the sample distribution. And according to central limit theorem, if your number of samples are quite large that you have taken as subsamples, so their distribution will be approximately, it will be a normal distribution, and it can give you almost 100% accurate prediction what you could have got by taking the entire population as your data for doing the prediction. Okay. But at the same time, it also tells you what should be the right size of the sample. There is a relationship between the population to the sample. But at the same time, it says that the sample should always be greater than 30, the N. If it's not, then it may not capture uh, each and every type of data values, and it might not give you the true picture of the entire population. Uh, so broadly, those things it says, and it also tells you what is the size of the sample. We'll see if there are some things which we should remember here. So sample size and the standard error. If you want to reduce the standard error, you have to increase the sample size. So that's a relationship. They are inversely related. If you want that all the population, or sorry, sample means should be at the same point, then the sample size should be quite big. But then we have to do a trade-off. If we are going for a big sample size, then you have to do a lot of surveys, which will take your good amount of time and good amount of resources. Instead of that, I can have too many smaller samples, and then I can also take the average of that, which can give me more or less the similar answer what I could have got to the population. So three things you have to look at. So either you can go for a big sample with lesser number of samples, but if you find that it's a difficult thing, then you can go with a good number of smaller samples, and it should be sufficiently good number. Like there are no researchers who say that it should be as high as 300 or so. But if you can't do that, then go with sufficient number of samples, and those sample size should be at least 30. Okay. So these three things you should remember based on the central limit theorem. But again, there is a problem with the population itself. If your population is not very big, then what needs to be done? Because from a population, when you start taking out sample and you are not making any replacement, so all those samples which will come later will have lesser choices to pick from, and that can bring the bias. Yes, because the ones which are picked as samples from the population in the initial time, they had too many choices. Think about a box which comprises of three different chocolates, and you are asking, the student to pick 10 chocolates. So the first guy who might pick 10 chocolates, he will have a better mix of the three different chocolates, but somebody who will be the 10th or 12th person who is going to pick, he may not get in the same proportion. Okay, there could be a bias that he will notice that one specific chocolates are more in number compared to the other chocolate. So that's where, to overcome that or to compensate that, we have to do something with the sample where we have to say that the error is higher, right? So we always assume that the error will be higher with the people who are looking or taking it later. And just to justify or compensate that, if my overall population is too small, we have to multiply it with a constant that is known as a finite population multiplier. So this needs to be done only when you are sure that the population is a smaller population. Again, we will define what is a small population, what is a big population, where we can assume a population to be a infinite population. And then we will also see what treatment needs to be done. Okay, all this are reserved for the next slide, which is now here. Finite population multiplier, often defined by the list of uh, all this, right? In the roster, how many people are there? Credit card account number, inventory product number, right? So, which as you will start counting the inventory number, lesser number of inventories will be left out. Yes, and same with the membership. So when you are randomly picking somebody or electing somebody for a level, okay, for take the very simple example in our NMIMS trust, right? That's Vicky. So they have different designations, like there is somebody who is the treasurer, somebody is the president, somebody is vice president. So when you have to pick from that limited 100 people or 200 or 500 people who are members in the SGKM, or 1,000 people, let's say. So for the president, you have a higher choice, right? But the next position when you are going for election, because one is already taken, you cannot again count him for the voting. So for the next selection, you have lesser options to pick from. Like that, if you keep on selecting, and if you are looking for 100 different people, so the 100% will have much lesser options, right, for selection compared to the first person who was selected, right? So for all such reasons, we have to do some compensation by multiplying with a finite population multiplier. Okay. So basically what we are saying is, so whatever I'm getting as a standard deviation or the standard error with that lesser number of people should be brought in parallel with the first person, right? And to increase that, I have to multiply something with those people, right? The smaller people. So a simple random sample of size n for a finite population of size n is a sample selected such that each possible sample of n has the same probability. So now we just want it to be assuming that they are all same. For that reason, we have to do this. Okay, so replacing each sample element with varmeta. So when we should really look at some of this. So replacing each sample element before selecting subsequent, right? So here we are Uh, so in the previous case, we were not replacing, but here we are replacing it. And this is called as sampling with replacement. Now you have equal chance for everyone, right? So sampling without replacement is the procedure used most often, right? We don't uh, replace the things, but for getting the best or accurate answer, right? So unbiasedness in the selection, we should be replacing, but that is not done, right? Normally, you have selected somebody, you will not put it back into the same box. Yes. Think about the game of housey. Yes. So what happens when we keep on picking one coin out of the box? Initially, we had the probability of picking something will be less, but as we will move around towards the end, there are very limited numbers are left. So the chances of getting a expected number increases there. Yes. So this brings a bias, right? So some numbers which are selected first had a lesser probability, but those which are going to get selected later will have a higher probability. So for doing that, so when the numbers are less, we have to multiply something so that this is not impacting. But then there is a case of infinite population. So every time you are replacing it, it's a lottery. So where every number, like if you're picking 0 as the first number of 1, so you have the choice of again getting a 0 or 1 in the next sequence number. So that is where you have an infinite population, right? A lot of people who have purchased the lottery, and whatever number you're picking, you have the chance for that. Okay. But all this are theory. I'm just leaving it to you for understanding. So same is with respect to the point estimation, where we are dealing about the number of defects. Okay. So here it's not a continuous, it's a discrete value. And those discrete values are considered as a proportion, right? So chances of just take the very simple example of point estimator as think about a Uber driver or a Ola cab driver. So for any specific day, how many customers he will get within a specific time limit is a point estimator, right? I can have 8 customer on a day. On the very next day, I can have 9. Someday I will have 6. Someday I can have 5. So those are discrete. Those are not continuous, right? In nature. So in such cases, again, it could be from a finite population if it's a small town or city. Yes. So the auto rickshaw guys in smaller villages or towns. So there it's a finite population, but if a city like Mumbai, Delhi, Bangalore, so there it's an infinite population because the population is very large. So getting your first customer and getting your fifth customer will have the literally equal probability. Unlike uh, in a smaller village, getting the first customer will have a lesser chance, but getting the fifth would be much higher because all these people have already moved or shifted to a place or a different location, right? So, and we have already discussed about the sampling error. I'm not discussing this all things, but now coming to understanding, right? What is a sampling error? Sampling error is just the difference. Okay, if you have taken a sample and how much the sample mean is missing out the population mean, that is the error. Okay, just like the standard error, what we had seen, standard error could be anything. It could be in terms of the sampling mean error, it could be sampling standard deviation error, right? Like this, or sampling proportion error. All these three together are considered to be the standard error. So we call the standard error of mean, we call the standard of first one as standard error of mean, the second one is the standard error of standard deviation, third one is the standard error of proportion. Okay, so when we take a sample, how much the sample is missing the population mean? It could be in terms of the average of the sample, it could be in terms of the standard deviation of the sample, it could be in terms of the proportion of uh, good parts in bad or overall, or the proportion of chocolates, right, within all chocolates that you get. So those are what is a proportion kind of thing, which are discrete. So first two are continuous. The third one is discrete. Now, how to handle the second part of what you're seeing is called as the finite population multiplier. So when we are calculating the standard error, you know this formula. The standard error formula is standard deviation by root over n. Okay. So this formula stands good if your population is infinite. Okay, it's very large. But if your population is not infinite, it's small, then you have to use a finite population multiplier. This multiplier will inflate this value because your population is not infinite. So there is always a chance of error, and that error I'm including here in my finding. Okay, so what you're noticing here is it's dependent on this sample size. Okay, so if your sample size is big, what is going to happen? If this n value is big, so n minus n will become small. And the smaller this value is, what you're doing. So this entire root over a very small number, when you multiply with this, obviously this value will come very small. Okay, but if your sample is small, this n will be relatively much larger than this n. And this value could be almost close to 1. And you will get this value. Okay, so that's how we normally deal with it. So with infinite population, we don't have to multiply this finite population multiplier. But what is that thumb rule which can define a population to be a finite population or infinite population? For that, we have this rule. It's the ratio of n to n, the sample size to the population size. Okay, so that can define which formula you should be using. If your sample, this n, is something which is much smaller, so how you can say it's much smaller to the population? So if you take the ratio of this n to n, so your capital N is in denominator. Okay, so if your sample size goes big, so then what is going to happen? If the sample size goes bigger, this value can go more than 0.05. So let's take some example here, a quick example to calculate. So if my population, okay, capital N, is 5,000, and if my small n sample that I've taken is 50, should it be treated as a finite population or not? So for that, we will just put these values here. So this is like 50 by 5,000. So what it will come? So 110 gone. 5 and this 5 cancel, and this will be point. There are two zeros, so one is for point and 0.01. Okay, so here this 0.01 is less than or equal to 0.05? Yes. So I can, in this case, I can treat this case as a infinite population, even though the number is finite in nature, right? So 5,000, but still, because this value is less than 0.05. Okay, but instead of that, if this n was just 500. Okay, so if it was 500, this value will be how much? This will be 0.1. So 0.1 is not less than 0.05. Okay, it's greater than that. Then I have to multiply this same value with the finite correction factor. So this is the finite correction factor, n minus small n divided by capital N minus 1 and whole root over. Clear? And then whatever we will get is your standard error. So let me just clean everything here. Now let's look at some simple problems here. So according to, one more thing, what the central limit theorem says that, okay, if the n is greater than or equal to 30 in a simple random sample, you can consider that to be a normally distributed, the sampling distribution. So this is a very standard thing, and most of the times when you will go for any market research or any kind of surveys, so the minimum requirement that they will say that you should have a sample of 30. Okay. But when the simple random sample is small, then you cannot really expect that the sampling distribution will always have a normal shape. Okay, so that is one constraint. So this comes from the central limit theorem. That's how the name has come. The central limit theorem. So the central limit theorem is that when exactly you will reach to the centrality, right? So in terms of the sample size. So here, 1 minute. This is what it talks about. So very simple example here. This is the sampling distribution of X bar, and the mean of all this is 990. And when you have to calculate it, so why we have gone with this here, because my n is 30, right? So with that, I've got the standard error value as 14.6. Okay, and this is the formula, the same formula you will be using in the sampling distribution, what we have done for the same formula which was used in the normal distribution. The only thing that has changed here is this standard deviation has changed by standard deviation by root over n. Okay, but now the next important thing is, if in exam a question comes, how will you find that whether this quotient is a sampling distribution quotient or it's a normal distribution quotient? Because the z value will change. If you are not getting this root over n, then means here I'm dividing by root over n and there I'm not in normal distribution. So the answer will differ. So how will you clearly understand that it's a quotient of sampling distribution or population distribution? Harshita, are you there live?
Yes, sir. I am. I'm just stepping out for a bit. My son is
Yes.
calling me.
Right. No issues. So just I'm just giving you this simple thing to quotient here,
Yeah.
because in your term and exam you might get a question, and where you may find that, yeah, what formula I should be using? Should I use the normal distribution formula where my standardized deviation, that Z score, uh, is calculated using X bar
Okay.
minus mu by the standard deviation, but in sampling distribution, it's root over n. So is this a problem of a sampling distribution or it's a problem of normal distribution? How will we differentiate that?
Okay.
So that's a question. So for that, I'm just giving you a couple of tips here. First thing, look for the word sample in the question. So if the word sample is not used, go straight away with a normal distribution formula. Okay. If the word sample is missing in the question, the second thing that you have to notice, if the sample size is not given, it's root over n, how we will calculate? Because this n is the size of the sample. If the question is not giving you the sample size, then also you can go with the population and you can just make a the normal distribution formula and just make a statement that the sample size was not mentioned in the question, and I'm assuming that the sample is sufficiently large. Okay. And that's where the overall distribution is taking a normal distribution shape, and I've used the normal distribution formula here. Right. So just to forward the logic why you have taken it, that is also important because there might be some evaluators or assessors who might think that no, because they go by the uh, whatever is the synoptic answer or something solution which is given, and if somebody is given a solution for a sampling distribution, they will straight away say that no, it's a sampling distribution question and you have not done it correctly. So just remember these two things. The first thing is the word sample is important, and the second important key thing is the size of the sample should be mentioned in the question. If that is not mentioned, then you cannot apply the sampling distribution, right? Then let's look at this with some numericals here.
Okay, sir.
This is for tire store. Suppose that the mean expenditure per customer at a tire store is $85, and the standard deviation is also given. So the population mean is given, the population standard deviation are given. Okay. If a random sample of 40 customers is taken, now look at here. The word sample has also come and the size has also come. So I have the small n. So what is the probability that the sample average expenditure per customer for this sample will be 87 or more? So this is a very clear sampling distribution coefficient. If this 40 was missing, then I can go on through the normal distribution. I have this is my mu, this is my x bar, and this is my sigma. But because now this 40 is here, I have to find something different because it's a sampling distribution quotient, because we are not looking at the population as a whole. Rather, we are looking at a sample of 40 and we are trying to come out with a prediction for this with regards to the population. Okay. If a sample that is taken here, I want to understand that with this 40 customer, can I get 87 or more money or dollars from them? Okay. So what is the probability of that? So the very first thing I have to understand is it's not just about, I have seen the n, small n, but is there a capital N here? Because in some questions you may find that even the population size is also given. But because we are just seeing that it's the recurring data and every day there is a recurrence. So I can straight away, I can assume that this is a infinite population. Okay. Anything which is a time series data can be treated as a infinite population because time has no limit. Okay. So nobody knows when the time has started and nobody knows when it's going to end. So anything which is time series data recurring every day and not as a cross-sectional data, I mean, on a specific day, you have picked multiple samples. So time series data, we can assume, right, in the future when you will deal with time series analysis, you can, by default, you can assume that this data are taken from an infinite population. Clear? But at the same time, because you have got this 40 as a number, it's a sampling distribution. So straight, what you will do, the Z value, you have to calculate Z equal to how much? What is my X here? 87 minus 85 by 9 by root over 40, right? So this is how I will get the Z value, which is nothing but this is 2 by 9 or 2 into root over 40 by 9. So this could be written as 4, 2 into 2, 4 root 10 by 9. So let's see what is this calculation exact value will come, because I don't have a calculator with me. But this is what you should be doing. So first thing is, yeah, you have to look at this number also, this 40 customer. According to central limit theorem, this is more than 30, means you can apply. You can treat this as a sampling distribution. So that qualifies it also, that you can use a normal distribution formula here. And we did this calculation and this value came to be around, this is a Z value, 1.41. So, you know how to use the Z table to get the probability value. I will show it to you 1 minute. Just give me.
Okay.
Yeah, I'm just showing it to. Just give me a minute. I'm showing you the Z table and okay, so are you able to see this Z table now? I'll just pull out one. Let me just zoom
Yes.
it. I can, yeah, just I'm increasing the size of it. Okay, so this is a Z table. Basically, it's a standard normal distribution table. So what is the standard normal distribution? Standard normal distribution is a table which has a mean of 0. Irrespective of whatever is the mean, you are just compressing that value to 0. And from there, you are looking at the deviation. So again, proportionately, your deviations will come down. So the reason why we look at the standard normal distribution rather than a normal distribution is this is free from any unit effect. Okay. So basically the 3 sigma thing and all that we were talking, right? If you scroll down here, the value of it. it's 3. Okay, so it will not be beyond 3. You will not notice here. The whole reason why it is we are assuming that in a standard normal distribution, okay, in 3.09, uh, it assumes that almost 100% of the data is covered. Okay, so everything is here. So total probability value is, it will start from 0 at the left hand side, and this is 100. So whatever value falls in this place is 100. This is 0. 50% chances on this side, 50% chances on this side. So that's how they have converted that, irrespective of whatever is the unit, your data is converted into unitary level, right? So that is in terms of the normal distribution curve that we had seen in the very start, where in the Six Sigma and all that, right, where we see there will be a value which is with respect to the meter. So you have to divide it with that meter and you have to bring it back to the non-metric form. And that's why we use that formula of the Z. So what is basically this Z is doing here, when I'm saying Z is equal to this X, sorry, X minus mu by standard deviation. So this is also, let's say it's in height or length, so meters. So this is also in meter. This meter and this meter is cancelling out. So we are converting this into in terms of the number of standard deviation, right? So how many standard deviations it's away. Rather than in the unit form, we just make it relative to the standard deviation. 3 stands for 3 standard deviation away from the mean, because this is 0 deviation. Got it? So the very purpose of using a Z table, why we standardize the normal distribution, because we can compare anything. This is free from meter, because this, if you're not using this meter, if you want to look at the deviation here, if it's not meter, if it's something in terms of kilometer, the difference could look very small. But the minute you convert that into centimeters, the proportional value could be much higher, right? So that's why we are removing it. So very similar to coefficient of variance, right? If you remember in the very start, why better than standard deviation? It was discussed because coefficient of variance removes that meter impact, okay, or the metric impact on the data or the deviation. And you can compare any two things. Something which is in a scale of temperature could be compared with something in terms of the monetary values, which is in dollars, or something in terms of the length value, which is in meter. So anything can be compared, and that's the beauty of this standard normal table also, just like in the equation of variance. Now let's see how we can find the value that we are looking for. So if I go back to the slide, so we have to look for the Z value, which is 1.41, right? So what is the probability with respect to 1.41? So Z greater than 1.41. Okay, that's what we have to look for. And to find that, we have to search. 1.41 is that much of standard deviation. So Z is 0 at this point. From here, we have to see how much is this 1.41 hours. Okay. So this is 0, 0. Now in this line, I have to look for 1. This is a 1. After that, I have to look for 1.4. Okay. This value is 1.40 and this value is 1.41. Okay. 1.41 is 0.42. Okay, so 0.42 is 1.41 corresponding value. But 0.42 will give you this area. So whatever is the shaded region, the probability of falling here is 0.42. Okay, but I want this area's probability. This is what is required. So how to get this value? Any thoughts here? How I can get this value? So going by the simple logic of simple normal distribution, which says that each half of this is 0.5 because total area is 1. So 1 when divided into two parts, each half will be 0.5. Okay. So that side 0.5 and this side 0.5. So total, this red area is 1. When I have to look for this upper side from here, I know this entire distance is 0.5. So the table is giving me the left-hand side. So up to the Z value, this value which came to 0.42. If I have to find the other side of it, what I have to do is I have to subtract 0.42 from 0.45, sorry, 0.5. So this is 0.5 minus 0.42. So we'll get something as 0.08. So approximately there is an 8% chance that I can make a sales of 87 or more dollars on a sample of 40. Okay. Is it clear? Harshita, did you got it right what we did here? How we came with this 0.08 value? Okay, let me just clear it and take you back to the slide. So if in any of okay, I'm just repeating it, what we did. I'm just going back to the PPT first, and then I will come back to the this table. So my population parameters are 85 is my population mean and the standard deviation 9. The sample size I got 40 and the sample whatever is the sample sales value that I'm looking for is 87. So when I put it into Z value calculation, 87 minus 85 divided by 9 root over 40, I got this value of Z as 1.41. Okay. I was just telling you how we should be looking at this 1.41 in a table that is a Z distribution table. So for that, so this is the tables of Z distribution. And in this table, the most important thing is we have to look at this graph because different tables have different things. So some graph will be showing the entire value from left to the right. So just look at the shaded area. So whatever we will find in the table will be the probability of falling in this shaded area. Okay, that's what we are getting. And just remember a couple of things here. The entire area of this standard normal distribution is 1, okay, which is 100%. And when we divide it into two parts, so because it's a bell-shaped curve, each side, it's 0.5, okay. So this side of 0, the probability is 0.5, and this side of the 0, the probability is 0.5. Okay, so with that, we have to search for the 1.41 value of the Z. So for searching this 1.41 Z value, apart from this highlighted values in the left, which is increasing as we are moving down. So just search for 1.4 here. This is 1.4. Okay. Along this row, my answer is there. But what is 1.41? The very first value is 1.40 and then 1.41, 1.42, 1.43, and like that. So 1.41 is in the second column. 1.4, and this is what is the second column value, that is 1.41, which is nothing but equal to 0.4207. Okay, so this 0.4207, what it really means is it's the probability of this area. Okay, so this 0 is my 85, 0 deviation from the mean, and this Z is my 87. So the probability of getting a return or a sales ranging from 85 to 87 is 42%. But my requirement is something which is after this 87. Okay, so this is 85 and this is 87. And the question is asking you that what is the chance of getting 87 or more? And what I've got, the probability 42%. 42% is for this part, the shaded part. Okay, so this part is 0.42, but if I have to find this part, so this can be calculated using this part is 0.5 minus 0.42. And it comes to approximately 0.08. It's slightly less than that because it's 0.4207. Okay, but I've just rounded it here. So which is nothing but 8% chance you have that you will make 87 or more dollars on a particular day with that number of people visiting your shop or something. Clear?
Okay, sir. Yeah.
Right? So this is what it is, 0.0793, because we just rounded it to 8%. Now, suppose that during any hour in the uh, large department store, the average number of shopper is 448. And its standard deviation is 21 shopper. What is the probability that a random sample of 49 different shopping hours will yield a sample mean between 441 and 446? Now, instead of a unique value, right, which is at an extreme, we are looking for interval which is in between. So now what can be done here? How to handle this? So how I can find it? Because here, if I have to plot it, right, this. So 448 is the population mean. Okay, so I am looking for something between this area, which is 441 to 446. Sorry. Okay. What I can do is the very simple rule. This line divides, the mean divides the normal distribution into, or the standard normal curve into two parts, and each part is the mirror image of the other part. Okay, so first time it's simple because on the right hand side we were looking at, but now we have to look for the left hand side. And for the left hand side, but the table will not change. The table will give you the values for the right hand side, right? So we have to consider that probability is same as the left hand side. Okay, so anything which is here, this area is same as this area, right? Same way, the next area will be same as this area. So for that reason, what you have to do is when you're calculating it, irrespective of the left and right side, you just assume that this is a mirror image. Okay, so only the sign is going to change. But now, first thing is I have to calculate the Z value, which is the difference between 441 minus 448 by sample is, sorry, standard deviation is 21 and root over 49. So why 49? I'm not multiplying it with finite multiplier because uh, this is greater than 30 as per the central limit theorem. I'm considering this to be a infinite population here again. So this will come as Z is equal to 7 into this 7, right? And this is also 749 root. Sorry, 7, 7, 49, yeah, by 21. So 1, 7, and this will go. So basically, this is 7 by 3. So 7 by 3 is equal to 2.6, right? So this is the Z value. So you have to first calculate the probability for 2.6 as Z. And then the other one, the Z is equal to 446 minus 448. Same denominator is going to be same, 21 by root 49. So this is nothing but 2, right? 48 and 6. So 2 by so 2 by 3 basically, right? So 7 and 7 will cancel, which is nothing but 1.66. Okay. So this is 1.66 and this is 2.66. So you have to calculate the probability values in the Z table for both of them. And then we have to take the difference. That will give you the answer. So let's look at the Z distribution now. So 2.66, go down, down, down. So 2.6 and 60, 61, 62, 63, 64, 65, 66. So 0.49, 61, and then 1.66, 1.6, 1.60, 61, 62, 63, 64, 65, 66. So 0.4515. So the difference of these two comes to how much? So 11 minus 5, it's 6, 5, 4, and then so 0.044 or 0.045, you can say. So 0.045 means 4.5% chances of falling in that range. Okay, so that's how we can look at it. So let's see in the presentation, the solution is there. So this is what we got. So this where, oh my bad, was my calculation wrong? 441 and 446. So minus not, how come, so 448, 441 and 446. I don't know what I had taken. So this 2 was 2 and that was 7, right? So I have to just check once, either this is incorrect or that. But we got this values like minus 2.33. And that's obviously this is different because in my calculation, okay, thank you. I'm just taking a break, Harshita. The feedback link is coming for you to give the feedback. So once that is done, we will continue. And then we're just left with one problem related to the proportion. And we can
Okay.
talk after that. Okay.
Okay.
Checking the calculation also. 441 minus 448. What is it? Just now they're posted. Okay, just check now.
Okay, got it.
Archita, once done, just let me know how we can continue. And I've just checked the calculation and I got it where I've gone wrong.
Okay, sir.
Is it done?
Yes, sir. Now.
Okay, fine. So I just making those correction right where I had just done the calculation error. So for the first one, how we got this 233? It's 441 minus 448 Z value. Okay, I'm just calculating that divided by 21 by root 49. This is nothing but 7
Minus.
by 21 by 7.
It would be -7. No?
Yeah, minus. Yeah, thank you. Yeah. It's normally we don't look at the sign. It's the area that means the probability.
Okay.
So irrespective of negative or positive, it's a case that no we are concerned with. Okay, but fine that you told me that's good. Now this is nothing but 7 by 3, and 7 by 3 comes to minus 2.33. Okay. Same way, the next one, z equal to, instead of 441, this time we have to take 446. Remaining all values are same, 448. 21 by root 49. So which will be minus 2 by 21 by 7. Which comes to minus 2 by 3. And minus 2 by 3 is minus 0.67 or 0.666, right? So you can write it as 0.067, right? So this is how we have got the second value also. So we have to look for this in the table. The Z table, so 2.33 here stands for 0.4898. Sorry, 2.30, 2.31, 2.32, 33.4901. Okay, and 0.67. So 0.60, 61, 62, 63, 64, 67, which is 0.2422. So if you take the difference of it, approximately, it comes as 0.24. So there is 24 chance probability of falling in that range. Okay, so that's how you have to interpret it.
Okay.
This is how it really looks like. So here we have converted it into standardized normal distribution. Okay, and this is in the proper table form, right, where actual values are taken. So this 448 is converted into 0, and from there it's only in the deviation form. 441 is 2.33 deviation, whereas 446 is at 0.66 deviation from the center. Okay, so proportionally, how many times it's no that far off? In the sampling distribution again, the proportion, how we calculate this P is X by N. So P hat is the sample proportion, okay? So sample proportion, how we get X is your number of items that is there in the sample, which you are looking for as success. Number of items for success is like, I have 100 items. In that, I want to search, right? I'm doing a QC that what is the chance of getting two defective? Here, successfully identifying two defective is my success, right? Even though that is a failure of the company, but for me, it's a success because my job is to identify it before it reaches to the customer. So that 2 is my X and N is the total 100. That is the size of the sample. Clear? So that is the proportion, right? So the defect that I've identified is 2 in 100. And that is P hat. So 0.02 is the chance of a defect in one sample I can derive. But now, when I use the sampling distribution here, for that, there are two things that we have to really understand, because we are not, basically this are binomial distribution, right? Anything which is discrete, but we are converting that into a normal distribution. It's a binomial assumption of a normal distribution, right? So basically the binomial is assumed to be a normal distribution, and according to central limit theorem, that's only possible. You can do such assumption when your sample size is sufficiently large, which is how to know which is sufficiently large. N into P and N into Q both should be greater than 5. So P is the proportion of the defect. Here in this case, let's take the simple example. If I have my sample size is 100, right? And my P is 1 minute. Where is that? So N is 100. The P that we got is 2 by 100. So 2 by 100 is 0.02, and Q is always N minus P. So basically, yeah. So when I calculate it again, and then I have to divide by 100, so that will be 0.98, right? So this is the probability of non-defective items. So now, if I have to check this N into P, 100 into 0.02, what it says that it will give you around 2, the number. So this is satisfying, which is 98, but this is not satisfying. It's less than 5. So I cannot assume that to be a central limit theorem. So it should be either a bigger value, that is 1,000 or something. Then only that is doable. Okay, so let's try with this. And then the denominator will be, instead of that standard deviation by root n, it will be PQ by root n. Okay. So the numerator is going to stay same. So numerator will be P minus P hat, P hat minus P, anything is fine, by root over, this will be your Z. And thereafter we will use the same Z distribution to calculate. So let's quickly look at one problem and then we can stop because it's 9:30 already. So I don't have this problem here, but I'm just telling you this is how it's done. Um, if you say that here for a proportion thing, the first thing that you have to remember is the population P. Okay, it's not the sample. The population is along this entire thing, right? Overall, what is that P value? So you have to use that P, then you have to subtract the P hat from that and then root over P of PQ by N. Again, because probably I have not used the example here because it's not covered in the asynchronous part. So you can be assured that this kind of questions you will not get in the term and exam and so on. Okay, so it could either fall with a discrete one or sorry, with the no distribution with which is infinite distribution or which is a finite distribution, but not with the discrete distributions like the proportion. Okay. So with that, shall we stop here? All good. Jita, I have just shared one case study also, which is related to a vehicle launch of Mahindra and Mahindra. Because
Yes.
of the time constraint, it's not. Just look at it. So if you find any difficulty in understanding with that, in the next session, I will share the solution also with you, or I will upload it. But we can just start tomorrow's session with that discussion, and then we will move to the next part, that is on correlations and regressions. Okay.
Tomorrow,
Yeah, tomorrow we have
do
it
we
at
have
10.
session?
Yes, we have it at 10:30.
Okay, 10:30 is tomorrow session. Okay,
Yes, yes.
all right.
Tomorrow session is at 10:30. So from 10:30 to 1 o'clock. Right.
Okay,
So,
sir.
okay then. Good night and take care. Hope we will meet tomorrow. And that is more related to even the you have one pending IA also, right?
Yes,
So,
tomorrow 9:30.
yeah. So that will cover that too. And apart from that, obviously, it could be an important topic from the term and assessment point of view also. Okay,
Okay, sir. Sure.
okay then. See you. Good night.
Thank you, sir.
And
Good night.
I'm just calling it.